Welcome to Lecture 28, in which we will discuss two-input NAND gate implementations of Boolean functions. And I don't believe this topic will take us very long, and so this will be a good opportunity for us to review a few ideas from recent quizzes that I want to make sure didn't slip by you. So let me first return to Lecture 24. Maybe it's 23. Whoops. Let me take a break. I'm having trouble finding what I want to. Wait just a second here. Okay, here's what I wanted to show you. This is on quiz number 23. We had this question. We said that suppose that in the dense coding algorithm all the steps are followed exactly as described in the book and in Lecture 23, except that the initial entangled pair that is distributed to Alice and Bob is 1 over square root of 2, 0, 1 plus 1, 0, instead of the usual 1 over square root of 2, 0, 0 plus 1, 1. And we ask, what will Bob measure when Alice wants to send 0, 0, when she wants to send 0, 1, when she wants to send 1, 0, and when she wants to send 1, 1. And the answer turned out to be, for this first one, when she wants to send 0, 0, Bob will he will measure 0, 1. And when she wants to send 0, 1, he will measure 0, 0. When she wants to send 1, 0, he will measure 1, 1. And when she wants to send 1, 1, he will measure 1, 0. In other words, in every case, his first qubit will agree with the first bit that Alice wants to send, but the second qubit will be exactly the opposite, the complement of what she wants to send. And so the observation that I wanted to make here is just a very simple observation that if Bob put an X gate, the inverter gate, on his second qubit before measuring it, then he would measure exactly what Alice wanted him to measure. So that was just a brief observation of how this could be straightened out. The next observation is a little bit more involved, but I think you'll find it interesting. And this deals with lectures 23 and 24. So let's start with 23. Now, lectures 23 and 24 are about dense coding and quantum teleportation. And the book described, and this was mentioned a little bit in our lecture, the book described how in some sense dense coding and quantum teleportation are inverses of each other. And I want to show that that idea extends to what we did in our quizzes, which might not have been obvious to you at the time. So let's go back here to lecture 23. Now I will remind you that in the dense coding algorithm, Alice is wanting to send a classical number, a 2-bit classical number. It is one of these four, 0, 0, or 0, 1, or 1, 0, or 1, 1. And in the usual dense coding algorithm, these transformations here are the transformations that she would apply in each of those 4 different cases. These are the transformations that she would apply to her first qubit of the entangled pair that she and Bob have. And so the transformations are in the order I, X, Z, Y. Now, our question in this problem at the end of lecture 23 was if Alice put these in a different order, and instead of I, X, Z, Y, if she put them in this order, I, Z, Y, X, and so if she put them in this different order, then what transformation here could Bob substitute for the C0 gate that he would usually use in the dense coding algorithm at this point? What transformation could he substitute that would allow him to end up getting the same results as he would when he uses a C0 gate here and Alice uses this order for the transformations, I, X, Z, Y. And you will remember you found this matrix, but what you might not have noticed was that the matrix that you found is exactly this matrix that we used in the problem at the end of lecture 24. And we said that there, where we're talking about quantum teleportation, remember that Alice now will apply first a C0 and then a Hadamard transformation to those first two qubits that she has. And we in our problem we said, well, what if instead of applying the C0, what if Alice applied this? So again, now in the quiz 23, we said that if Alice applied her transformations in a different order, what transformation could Bob substitute for C0 in order to undo that? And this turned out to be the matrix. So now we're supposing that Alice uses this instead of the C0 gate in the quantum teleportation algorithm, and lo and behold, we found out that if she does that, and Bob wants everything, remember we said the question here was, if Alice conducts the rest of her steps as described in the lecture, what transformations should Bob apply in order to have the the desired result here, that the unknown state is indeed teleported from Alice to Bob? And you will remember that the answers here turned out to be exactly these, I, Z, Y, X, instead of what Bob would usually have, which was I, X, Z, Y. So this makes it look even more like the quantum teleportation and dense coding algorithms are inverses of each other. So those were two notes that I wanted to make sure you had caught, two observations. And this last one, you might need to think about it a little more in a little more detail, but you'll see, I think with a little bit of thought, you'll see, I'm hoping, what I'm talking about there. And so there is one more observation I'd like to make, and it concerns the lecture at the end of lecture 26. We have this problem here. This was the second problem in lecture 26. And I would like to, well, you will remember that I gave you the hint that you might want to use the approach of just having a truth table, and that way you could identify what beta is. Now I want to show you another approach that is more efficient. So let's see how this goes. Okay, so here's the problem again. I've transferred it to today's lecture, lecture 28. And the way that I'm going to, or the way that I'm going to approach this is the following. So let's start with an observation here. Let's say that we have 3 bits, which we can call X, Y, and Z. And the first 2 bits are controlling that third one. So we know that the output on these 2 lines will be X and Y. But the output on the third line will depend on the values of X and Y. And if we constructed a truth table for this, it would look as follows. We're going to have X, Y, and Z, and then I'll call the output, I'll just call that out. But I also want to calculate one more function, and that's XY, and you'll see why I want to calculate that in just a moment. Okay, so now we're going to go through all the possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And now we calculate XY in each case, and so that's 0, 0, 0, 0, 0, 0, 1, and 1, because we get that information, or we get this result because 0 ended with anything at 0. And so in each of the first 6 lines, either X or Y, or both X and Y, are 0. So that's why we get 0 in the first 6 cases. But in the last 2 lines, X and Y are both equal to 1, and therefore XY is equal to 1. And now we want to calculate what out will be. Now, unless X and Y are both equal to 1, out will be equal to Z. So we can just put Z, we can put the value of Z, which of course is this column right here. So we get 0, 1, 0, 1, 0, 1 for the first 6 values of out. And now for the last 2 values of out, well, remember that in those cases, when X and Y are both equal to 1, then this last, the value on the Z line will be inverted. So this 0 will become a 1, and this 1 here will become a 0. And now what I want to encourage you to do is to look at these, at the 2 columns here, Z and XY, and also at out. When Z and XY are both 0, out is 0. When Z and XY are both 1, out is 0. Here again, when Z and XY are both 0, out is 0. when z and xy are both 0. Out is 0. But if z and xy are different, if they're 1 and 0, then out will be 1. 1 and 0, out will be 1. 1 and 0, out will be 1. 0 and 1, out will be 1. So we see that whenever z and xy have the same value, out is 0. But whenever z and xy have different values, then out will be equal to 1. So what is out? Out, so we can say we observe that out is equal to z exclusive for xy. And just to make sure you recall what that means, I'll put it up here. A exclusive or B is equal to A and not B, or not A ended with B. And so you can see that, for instance, if A and B are both 0, okay, if A and B are both 0, then the first term goes away because A is 0, the second term goes away because B is 0, so everything goes away if A and B are both 0, it's equal to 0. If A and B are both 1, the first term will go away because because B is equal to 1, so not B would be 0. The second term will go away because A prime would be 1 prime would be 0. So A exclusive or B is equal to 0 if A and B are both 0 or if A and B are both 1. However, if they are different, if A is 0 and B is 1, let's say, then the first term disappears, but the second term is 1. And on the other hand, if A is 1 and B is 0, then the second term goes away, but the first one is 1. So A exclusive or B is equal to 1 when the two Boolean variables have different values, and 0 when they have the same value. But we just observed that out has that same relationship to z and the product of x and y. So this means that out is equal to z ANDed with xy prime ORed with z prime ANDed with xy. And so using that information now, let's come back up to your quiz. This was the last problem on the 26th quiz. And we have two C0 gates here. So if we label, if we first of all calculate that, maybe we can call that alpha. And so alpha would be equal to, now in this case, what's coming in is 0. So we have 0 ANDed with xy prime. And then that gets ORed with 0 prime ANDed with xy. And what does that give us? Well, 0 ANDed with anything is 0, so the first term goes away. 0 prime is 1. 1 ANDed with xy is just xy. So alpha is equal to xy. And now we apply the principle again here at this point to get beta. Okay? So we'll get xy ANDed with xz prime, and then that gets ORed with xy prime ANDed with xz. And let's see what that will give us. Okay, here we'll have the xy, but what is xz prime? Well, we can use De Morgan's theorem to say that that's equal to x prime or z prime. And similarly here, xy quantity prime is x prime or y prime, and that's ended with xz. Now if we multiply this out, well, xy ended with x prime. Since this has x in it and that has x prime, that will be 0. So we will get xyz prime from this first term, and similarly over here, x prime ended with xz goes away, but we do get an x y prime z term here. So x y prime z. And you notice then that this answer agrees exactly with answer B. So this is how you could have done this problem without the use of the truth table. So that catches us up on some observations I wanted to make about recent quizzes. And now we'll get into today's topic, which is the two-input NAND gate implementations of Boolean functions. Okay, so as we said in our last lecture, we want to do things as efficiently as possible. And I want to just try to teach this topic through an example. So let's suppose that we had f of w, x, y, z is equal to w prime x or w x y prime or w x y z prime. This is an example. Now if if we were challenged with let's say implement this in an efficient way using two-input NAND gates. Now, one observation before we go any further. We found out that right up here with this example, we found out that, for instance, if we have 0 coming in here and we have the x and y lines up here as our control lines, then our output for alpha will simply be xy. So we can easily, with the Toffoli gate, we can easily implement AND. Furthermore, if we make this 1 a 0, then instead of getting xy, we would have gotten not xy. And so we can also implement NAND. So it's easy for us to implement either AND or NAND with the Toffoli gate. And so if we can get a classical circuit that's all NAND gates, then using Toffoli gates where we have NAND gates, we can easily get an efficient or a similarly efficient quantum circuit. So that's the idea. That's why we're motivated. The Toffoli gate gives us AND and NAND very readily, and so that's our motivation for studying NAND gate implementations in the classical case. So let's say that we were challenged with trying to find an efficient way to implement this function using only two-input NAND gates. Well, the way that I recommend that you proceed is as follows. First of all, we can use the Klein-McCluskey method to write this function in a minimal fashion. Now, Since the Quine-McCluskey method is involved, I won't go through all that again, but let me remind you of what the steps would be. So we would first of all want to, we're not quite ready to use the Quine-McCluskey method on this because we want all of the beginning terms to be min terms. In other words, we want all the beginning terms to have all of the independent variables. And so this one is missing y and z, this one is missing z. So how can we remedy this? Well, we would simply rewrite f in this fashion. We could say this is w prime x, and remember we can always AND a term with 1 without changing its value. So we could AND this with y or y prime, and we could also AND it with z or z prime. Now then, when we multiply all of that out, we will get 4 terms, which of course is a lot more involved than this. We'll get 4 terms, each of which will have 4 variables in it. So that's 16 literal appearances of the variables rather than just the 2 we have here. So that certainly is a lot more involved. But then hopefully when we go to the Quine-McCluskey method, that might help us to write our entire function more efficiently than this. Okay, so again, then if we're intending to use the Quine-McCluskey method on this function, we would AND w prime x with y or y prime and with z or z prime, because both y and z are missing here, missing in so much as they're not present to give us min terms, which is what we want as the beginning step for the Quine-McCluskey method. Okay, here for the second term we would just AND it with z or z prime, and the last term is a min term. It has all the variables present, so we don't have to AND it with anything. So so after writing this down, what we would do is multiply all this out, and then we would have 16 terms here and 2 terms here, so there'd be 18. We would have 19 terms all together. Now some of these would probably condense into each other, and so if that happened, we wouldn't have to worry about any terms like that. Actually, let's see, would any condense? Maybe. Actually, I'm not sure that any terms would condense, because every term coming out of here would start with w prime x. Let's just see this for a moment. Let me take a quick break. Okay, I see now where my problem was. This would give not 16 terms, but 4 terms here. So we'd have 4 terms coming out here, and 2 terms coming out here, and 1 here. So 4 and 2 and 1, we would get 7 terms altogether. And indeed, none of those terms would combine with each other, because all of these terms that would come out of here would have w prime x. All the terms coming out here, and notice that no other term has w prime x. All the terms coming out of here would have wxy prime, and that certainly doesn't match that, and it certainly wouldn't match any of these. And so all of these 7 terms that we would get, the 4 from there, the 2 from there, and the 1 from there, all 7 of those terms would be different from each other. So we wouldn't have any combination there. But then once we got those 7 terms, then we could go through, since those would all be min terms, we could then go through the Quine-McCluskey method, and hopefully we would end up with an expression for f that was even more efficient than this. Now that might not be the case, but perhaps it would be the case. So let's just, now again, I'm not going to go through all that because the Quine-McCluskey method is rather involved, so we won't do that. We've already looked at that most recent lecture. So we'll just we'll say assume that the minimal sum for f is f of w x y z equals, well, actually, let me just stop for a moment and I can find this quickly offline. Actually, I'll tell you what, I won't even do it offline. Okay, instead of doing it offline, I'll do something that is more that is quicker than the Klein-McCluskey method, and this will be a review for some of you. And if you don't understand what I'm doing here, don't worry about it at all. It's just called the Carnot-Mapp method. So if I were going to use the Carnot-Mapp method for this, I would proceed as follows. And again, I stress, if you don't know about the Carnot-Mapp method, I'm not trying to teach it here. I'm just, for those who want a brief, for those who've already seen it, this will be a very quick refresher. And if you haven't seen it, don't worry. The Klein-McCluskey method is a better method for you to learn about because, as I said before, it is applicable to functions of more than 5 independent variables. But again, for those of you who want a quick refresher, so we're going to list all the independent variables, wx on the horizontal, on the vertical axis, yz on the vertical horizontal axis, and now we want to color in, or we want to fill in all the terms we have. So w prime x will be this 1, 1, 1, 1, because that's the we have 0 for w and 1 for x. So that's the w prime x. It'll lead to those 4 terms, and that corresponds to the 4 terms that you would get if you multiplied this out. wxy prime is 1, 1, and then 0 for y, so we get these 2 terms right here. That's wx y prime. And again, these 2 1s correspond to the 2 terms you would get when you did this. And then wx yz prime, okay, wx is this row, and then yz prime would be a 1 over here. So now this is the Carnot-Mapp, and now we want to see what our groupings will be. And so we have 16 cells altogether. Are there any groupings of 16 ones? No. Are there any groupings of 8 ones? No. So what about groupings of 4 ones? Yes, we have 2 such groupings. One of them is right here, and so, and these are going to be our prime implicants. And I'll just draw a little sketch above each one that I identify. So that's one grouping, and that is the grouping x, y prime. Another grouping of 4 would be this. And that is the grouping w prime x. And those are the only groupings of 4 that we have. Oh, no, sorry about that. There is one more grouping of 4, and it's these 2 right here grouped with these 2 right here. That one's easy to miss. That's another reason that I prefer the Klein-McCluskey method, at least for some cases. I know it's more involved. It takes a lot longer, but you see, we almost missed, or at least I almost missed, that grouping of 4 with the Carnot-Mapp method. But with the Klein-McCluskey method, it's really impossible to miss things. You know, it's just sort of automatic. Okay, so what about this last grouping of 4? That consists of these 2 and these 2. Well, that will be, the name for that one will be x z prime. Okay, so those are the prime implicants, and then when we want to identify the essential prime implicants, well, the last one that we just identified, we see that this is an essential 1 cell, and this is an essential 1 cell, and this is an essential 1 cell, and that's enough to tell us that all of the prime implicants are indeed essential prime implicants. And therefore, the minimal sum for this function, there's only one, and it is f of w x y z equals xy prime or w prime x or xz prime. So I encourage you, if you well, first of all, let me repeat one more time. If you didn't understand what I did just in with Cardinal Maths, don't worry. What you want to learn is the Quine-McCluskey method. But here you have a good problem. Now that you know the answer for this, you have another good problem to practice with the Quine-McCluskey, and I don't think that this one will take too long, so I encourage you to do that. But now then I don't have to say assume anymore. We'll say the minimal sum expression for f is, and we have f of wxyz equals xy prime or w prime x or xz prime. And again, that's obtainable through either the Cardinal-Math method or the Quine-McCluskey method. And one final note before we proceed. This is a minimal sum, which means that it is the this is called a sum of products expression here, because you can see the pluses, so it is a sum, and each term that's being added together is a pure product of the Boolean variables. And this is the expression that would minimize the number of literals, which is the number of appearances of these variables. This doesn't necessarily end up giving us the fewest number of NAND gates in our final implementation, but it's a good bet that it will come close. So this is what we'll do, is we'll use, if you're challenged to find an efficient implementation of a 2-input NAND gate implementation, then what you should do first is use the Quine-McCluskey method to find a minimal sum, and then once you have that minimal sum, then what do? So we'll say, now how do we implement this using only 2-input NAND gates? Let me make sure you understand the difficulty. Right now, if you implemented this directly, well, to implement this, we would need an AND gate. To implement this, we would need an AND gate. To implement this, we would need an AND gate. And then once we got those 3 terms, then we would need a 3-input OR gate to OR them all together. We don't want to do that. We want to use only 2-input NAND gates to implement the entire function. So how do we do it? Well, my recommendation to you is the following. Okay, we write down this function, xy prime, or w prime x, or xz prime, and we make this observation. That function is equal to itself complemented twice. Now, you'll see why we want to write it in that way in just a moment. So what we're going to do is consider this to be the following. We'll have xy prime, or w prime x, or xz prime, and then another prime outside. Now the prime on the outside we're going to leave as it is, but the prime on the inside of the bracket we will get rid of using De Morgan's theorem. Now De Morgan's theorem, again, as we observed in a previous class, it says that the complement of a sum is the product of the individual complements. So we have xy prime ANDed with w prime x prime ANDed with xz prime. Again, the complement, remember the prime is complement, so the complement of a sum is the product. See, these are all ANDed together now, rather than being ORed together. They're ANDed together, is the product of the individual complements. So we have the complement of this first term, the complement of the second term, and the complement of the third term. Those are all being ANDed together. And so that is equal to the term in the brackets, and then outside the brackets we leave that exactly as it was before. And notice now that if we look at this is a two-input NAND here. We are ANDing and then complementing, so that's NANDing. We are NANDing together x and y prime. Here we are NANDing together w prime and x, and here we are NANDing together x and z prime. So this can be implemented, assuming that we have all the variables in both their complemented and uncomplemented forms. Then this can be implemented with a two-input NAND. This can be implemented with a two-input NAND, and this can be implemented with a two-input NAND. And let me also add that if you're troubled by that stipulation that we have access to the complements of the variables, if you don't like to assume that, if you like to assume that we only start with w, x, y, and z, well, that's fine as well, because we can easily put the x gate, the inverter gate, or on a line to get the complement of a variable. So it would be easy for us to get this y prime from y. It'd be easy for us to get w prime from w, and easy for us to get z prime from z. And then once we got those primed variables, then we can, using the Toffoli gate, we know that we can implement this NAND function. And here's our two-input NAND, here's a two-input NAND, and here's a two-input NAND. Can you see what the problem is? There's only one problem here before we can finish. So take a moment to look at that and see if you can identify it. Well, again, this can be implemented with two-input NAND. This can be implemented with two-input NAND. This can be implemented with two-input NAND. But how do we implement this? Because this is three terms that we want to NAND together. And but we're supposed to use only 2 input NAND gates. Well, if we're thinking about Toffoli gates, we know that Toffoli can be used for either AND or NAND very readily. And so with the Toffoli gates, what we could do is we could use the Toffoli gate to AND these two together, and those two together. And then once we got that result, we could then AND that with this, which we would obtain with another 2 input NAND gate. And then once we got all that, we could invert that, again with the Toffoli gate, to get this final function. Since that is really, what I've just said is what we want to think about, because our ultimate goal is to develop quantum circuits, and that's where we'll be using the Toffoli gate. And so I think that is better to come up here. Let's just change the title of this lecture a little bit, because I think that it'll be better for us to just think of it like this. Let's say, implementation of Boolean functions using two input AND gates well, let's just say, we'll go ahead. We'll say 2 input NAND gates, 2 input AND gates, and inverters. This will be a better title for us. It's a more accurate description of what we want to do, because actually down here with this problem we were working on, we could indeed, it is possible to put all of this in terms of only 2 input NAND gates, rather than using the fact that this is an AND, and then we could calculate that and then AND it with this and then invert. We could do it all NAND implementation, but that's really not consistent with what we will want to do then with the Toffoli gates. So let's just, since the Toffoli gate after all can be used for AND or NAND or for an inverter, and so everything we have up here, all these possibilities that we've allowed now in our title, all of those are covered by the Toffoli gate. So let's just go ahead and keep all of those. And so now then, just to make sure that what I said earlier was clear, so what we will do here is we'll have x, y prime, that will get NAND together with a 2 input NAND gate. W prime x will be NANDed together, and then with a 2 input AND gate, we AND those together. Once we get that result, we will AND that with x z prime prime, which could be obtained with a 2 input NAND gate. Now we AND these two things together with a 2 input AND gate, and then finally invert it. So we have NAND NAND, and then all this is AND, this is NAND, and then those are AND, actually no, we don't have to do it that way. We could do it like this. We could NAND. That is, after we get the AND of these two and we get the NAND of these two, then we can NAND, two input NAND for all of that to get our final result. So that is how we can take a function and write it in an efficient way, implement it in an efficient way using two input NAND gates, two input AND gates, and inverters. And the good news is that all of those can be implemented with Toffoli gates. So now let's look at some problems. Okay, so we'll have one in-class problem on this idea. And the question is, which of the following are valid implementations of the function f of wxyz equals w or x ANDed with y or z? And these are the four choices. And I'll give you a hint that more than one of these is correct. And so you should circle all of them that are correct, or all of them that are valid implementations. And one other last observation is that, well, actually two things. You do not need to use the Klein-Mikulewski method to obtain the valid ones. And in fact, you don't even really have to use the methods of this section. You could just check the truth function, the truth table for each of these. Remember that if for each one of these, if they disagree, if they have a different value from f for even a single one of the 16 different combinations that w, x, y, and z could assume, then they're not valid. So take a look at these and find out which ones are valid implementations of this function, and then we'll have another problem along these lines in class. So that concludes this lecture, and good luck.